involved very heavily in the CGEM, Coronal Global Evolving Model project. His talk is Improving Understanding of Magnetic Features from HMI Vector Field Measurements on SDO. Brian, I'll give you a warning at 15 minutes or at 12 minutes, and then you can try and finish up in 15. That'd be great.
Thank you, Todd. Can people hear me and see my screen?
Yes.
Great. So I was asked to talk about a few ways that HMI has helped us understand vector magnetic fields and structures on the sun. And I excuse me, don't have too much time, so I had to think about which areas I could cover, and I'm certainly going to omit a lot of things that are important to many people, for which I apologize. But so I'm going to try to hit 3 areas. The first of which I think is important to me in my research was the estimation of the Poynting flux, the transport of magnetic energy from the solar interior outward. And this was enabled by HMI's vector magnetic capability and full field of view and high cadence and then high duty cycle. And it's relatively high cadence. This particular combination of things, individual instruments had subsets of these, but not everything in one package. And I think that was very important. Another area that I think is very important that I will talk about is ribbons associated with, flare ribbons associated with flares, and particularly the magnetic fields associated with those ribbons. And a key point there was that both HMI and AAA were aboard SDO. And so we could now co-register the ribbons from AIA with the magnetic fields from HMI. And we weren't able to do that so easily before. And I think that allowed some major progress. A third area is flare-associated magnetic field changes. And again, this relied on the vector magnetic capability, field of view, cadence, and again, that high duty cycle. And then I'll talk very briefly about some things we might study in the future. I think some of the results in item 2 there about flare ribbons indicate that the soft X-ray heating in flares differs in quantitative ways from the steady heating outside of flaring intervals. And I think we might learn something about coronal heating from that. And I also think polarity inversion lines are special places on the sun where interesting things happen, but they're difficult to study. And maybe we could learn more with DKIST on those. So first, as kind of a high level science goal, I think it's important as a community for us to be able to follow energy as it emerges from the solar interior, is transported from the solar interior out into the corona where it can do things like drive flares and CMEs. So that's very scientifically interesting, but it's also practical because if we could follow that energy and quantify it, we could have an energy budget and we could probably incorporate that into forecasting tools. This outward pointing flux, you might recall, depends on the electric field. And in the ideal MHD approximation, that electric field is related to velocities, basically the transport, the bodily transport of magnetic fields. And HMI crucially enables us to with its vector magnetic field to quantify this. And if I write out the mathematical expression for the rate of change of energy in the corona, magnetic energy, that's the pointing flux across the surface. Basically, I'm going to ignore what's going out into the heliosphere. And then I can do some vector manipulations and I can see that I need to know the horizontal magnetic field and some velocities or electric fields equivalently. And so it was tough prior to HMI. We didn't have routine sequences of vector magnetograms with full disk coverage. And, but in order to do this, you know, the game here is I have to estimate this electric field that shows up in the pointing flux. And we can do that with Faraday's law, which relates that electric field to changes in the magnetic field. I don't have time to go into too much detail here, but there's an important point that I think people should absorb. We're essentially using the time rate of change of magnetic field to infer E. So I'm kind of uncurling this equation. So that means there's basically an unconstrained part of the electric field. Any part of the electric field that can be represented as the gradient of a scalar potential won't show up. We can't constrain that from those magnetic observations alone. And this is very important. A lot of people might think this doesn't matter, but if you think about it very much and you do tests and stuff, you can find out that it does matter, as several authors have argued, and I've listed a couple here. But 2 pieces of information from HMI do a better job of constraining this electric field. One is that we could, when we have information about the time rate of change of the vertical electric current, what I'm calling JZ here, I guess it should really be J radial. That's useful information. And then the Doppler velocities, particularly along polarity inversion lines from HMI, are also very useful. So practically, HMI enabled us for the first time to do things like make plots like Ying Liu and Pete Schuck did here, where they've plotted a time series of energy being transported across the photosphere, and then you can integrate that in time to get a cumulative amount of energy that's been injected into the corona across the photosphere. We could do this for short bursts of time before, but here they've done it over something like 120 hours, several days. We couldn't do that before HMI. And then we could also do things like make maps of the Poynting flux and find out where the Poynting flux is coming. And you can see here that there's some Poynting flux coming across this polarity inversion line here. Again, polarity inversion lines are sites of flux emergence, and so interesting things happen there. But a lot of work in this area remains. We've come up with techniques to estimate these photospherical electric fields, and we can use this for modeling in the CGEM model, which Todd alluded to earlier today and published a paper on recently, actually. There's ongoing work there for coronal modeling, and you can do data-driven MHD modeling, and I believe Bill Abbott is giving a talk next week in this forum. There is one challenge though, and I think this should be a longer term goal. We'd like to be able to relate specific coronal events to episodes of energy and helicity being brought across the photosphere or wherever we can measure it. If we can measure it higher in the atmosphere, that would be fine. So that we can really tie the coronal responses to the inputs. I think this is a good long-term goal, and I don't think we're there yet. Another topic I'd like to talk about is flare ribbons, and I apologize to the AIA team. I didn't have an AIA image of ribbons lying around, so I grabbed one that was handy, which was from the Inode SOT. And so here we see some ribbons associated with the flare. You can see they're kind of extended in one direction, and they spread out with time in the other. And these are generic features of most eruptive flares. We sometimes see stealth events, but those are more rare, I believe. And these fit within what Hugh Hudson might call a standard cartoon of how eruptive flares work. There's some reconnection in the corona, and post-reconnection fields or particles along those post-reconnection fields are accelerated and impact the lower layers of the solar atmosphere by Bremsstrahlung and generate emission there to make what we see as flare ribbons. We can overlay contours of those ribbons onto HMI magnetograms, and we can find basically the magnetic flux that was swept out across the surface. And we believe there's essentially a one-to-one mapping between those magnetic fields and reconnecting fields in the corona. Some people have argued it might be a 2-to-1 mapping, but not too worried about that, or a 4-to-1. It's definitely a 2-to-1 if you're going to take unsigned flux. I'm sorry, something just beeped on my computer. Apologies for that. But a key point here was that the combination of AIA and HMI on SDO enabled doing this for thousands of events. A very important paper, in my opinion, that was published a decade before involved only 13 events. And the reason the sample was so low was that Zhang Chu and Vasil Yurchishin had to search H-alpha observatories all over Earth to find people who happened to have caught flare ribbons for particular events and then co-register those. And that was very time consuming. Masha Kazachenko was able to do this for thousands of events. And when you do things for thousands of events, you can make correlations like this, which is the amount of flux in flare ribbons versus essentially GOES classes on the vertical axis here. And this is the rank order correlation coefficient. It's not the highest possible correlation coefficient that one will see, but in solar physics, that's a pretty good correlation. And you can do things, you can find this power law dependence. To me, an interesting thing is that this disagrees, and I think it disagrees significantly depending on how these are estimated, but I believe the difference here is statistically significant with steady soft X-ray emission that was studied by George Fisher et al. A couple decades ago. And so I think this might indicate that there are ways in which steady heating, studied by Fisher et al., differs from flare heating, as characterized by Masha Kazachenko and collaborators. And so I think that's an area for future study. Another area I wanted to discuss were flare-associated magnetic field changes. I think HMI has helped us make progress here. This might be the first solid observation of such a change. One of the problems is that during flares, the line can be affected, the spectral line used to infer the magnetic field can be affected by the flare. And then you have this magnetic field measurements are noisy, especially for vector magnetic fields. So you have this jaggedy line here, but you can see this is the flare emission line. You can see there is what looks to be a statistically significant change that persists after the flare. So it's not a transient associated with emission during the flare. More than a decade after this, Jeff Sudol and Jack Harvey published a statistical study of these kind of changes with Dong, which was due to its high duty cycle, was able to observe many flares and rapid cadence, so you could get many measurements and see these kind of stepwise changes. And as I said, I think HMI played a role in improving our understanding here. I believe it's fair to say that reports of these changes were viewed skeptically. It might be a euphemism for how some people thought about these changes in the early decades. And Haiming Wang, to his credit, persisted in the face of some criticism about these. These magnetic changes were infrequently observed, and their morphology was hard to understand. The magnetic field got stronger in some places and weaker in others. And usually we only had line of sight data. So it was hard to interpret what was going on. I think major progress was made when Hugh Hudson collaborated with George Fisher and myself to publish a paper. Hugh pushed us to do this. This was basically Hugh's idea this built upon his idea of coronal implosion, that the whole coronal magnetic field should deflate if its overall energy is lowered. And he argued that, and we made a cartoon, which may be the most important thing you could do, that the magnetic field ought to get more horizontal after a flare, that these are the types of changes we ought to see. But there was one other thing that Hugh put in that paper, and he and I have argued about this for decades. I saw he was on the chat, so I'm glad he's here to hear this. And he was building on something that Don Melrose had argued, that vertical currents shouldn't change during flares. And I don't think this is based upon a sound interpretation of what's going on. But HMI actually enabled us to see this. And these are a couple panels that Masha Kazachenko prepared probably about a decade ago and published a couple years after that. But you can see these whorls of horizontal vector magnetic fields associated with essentially vertical currents. And this is a pre-flare magnetogram. And on the right, there is the change in those horizontal magnetic fields shown as arrows. And one thing you can see was that a counterclockwise whirl before a flare has a clockwise change in its horizontal magnetic field during the flare. And similarly, a clockwise whirl before the flare has a counterclockwise change. So this is really the unwinding of a twisted flux tube corresponding to a vertical current decrease. So I think HMI really made things more clear here. And here's we might say a light curve of JZ from Gordon Petrie from the same event. And you can see there's this kind of significant change in JZ, and this is the flaring interval. Another thing you might note, however, is that the JZ seems to kind of return to its pre-flare levels. So there's some speculation here that the sun's solar interior can act as a current driver or a reservoir of twist that can be used to refill the coronal twist. And this was an idea developed by Longcope and Welsh a couple decades ago about what would happen if there was a decrease in essentially twist in the corona. There would be a rarefaction wave of twist launched into the interior, and the interior as a reservoir of twist would refill the corona. But this also leads to a prediction that Yang Liu and others have made, that we should see a post-flare increase in the flux of magnetic helicity as the corona refills with twist. And Yang and I are collaborating on that now. Now, I don't have time to study all the different facets or ways that flares can cause magnetic fields to change. And there are many other authors that I haven't mentioned, Cheng Liu and Sanjay Gosain and Shudong himself talking about this. But one area for future work, yes.
You have about a minute.
Thank you. One area for future work is to kind of redo this analysis of Fisher et al. And look at EUV heating across scales, things like X-ray bright points and the whole disk, and find out how that scales and see if it obeys a similar scaling. There was also work done on this with Jack Ireland and Andre Fludra. Harder work here is to, I think there's evidence that there is sort of enhanced core heating along polarity inversion lines, and you can see it in hotter AIA lines. And so I think polarity inversion lines might merit further study. And there are interesting things about the magnetic fields along sheared polarity inversion lines that I think merit study. Another feature about polarity inversion lines we've looked at, primarily Amy Norton has looked at, I was a wee collaborator, was maybe oscillations along polarity inversion lines, but I can't really address that now. So I'm just going to leave you, I look forward for more from DKIST there. I'll just leave you with my closing slide. I had 20 seconds left, Todd.
Thank you, Brian. Yeah, I was trying to just keep you on time, and I appreciate it.
Yeah, no, I understand.
It's very nice. It's always harder when you're doing it online, I think. Yeah. We have a couple questions from the chat. Both of them are that I've seen so far about Poynting flux. And so Hugh wonders if you can ever see a downward directed Poynting flux.
The answer is yes. I've seen them, we have seen them along polarity inversion lines. We've seen them in sunspots. I've seen them in quiet sun, in plage. There are regions where there's a positive flux, a region where there's a negative flux. You kind of have salt and pepper in plage. But we have found cases where that flux predominates, the upward flux predominates.
Second question from Sanjeev Tiwari. Nice talk, Brian. I know you've estimated Poynting flux using SOT data. Have you tried doing it with HMI? I think the answer is going to be yes.
Yeah, that was the paper that I'm trying to get my full screen here, and I can't figure out how to do it because I don't use Zoom often enough. That was in collaboration with Masha Kazachenko. We did that. Masha kind of took the lead on that, but George Fisher and I were heavily involved in making her life more difficult by telling her to do things different ways.
How does the estimation of Poynting flux depend on spatial and temporal resolution of the data?
That's a good question. I think there are two kinds, mentally, I think there are two kinds of Poynting flux. I think there's a kind of a ubiquitous background, short time scale, short duration Poynting flux that might be associated with waves or just properties of turbulence that's kind of always sending energy up. But I think there are larger spatial scale, longer time scale types of Poynting flux that are probably, have to do with the emergence of new flux or kind of steady twisting motions or shearing motions acting on pre-emerged flux. So if you zoom in with resolution, you'll get that smaller scale stuff going on, more wiggles on top of your larger secular variations.
Okay, thank you. And Valentina Zarkova points out that she did an investigation of the magnetic field change during solar flares and that she published in 2005 in JGR. And there's a link in the chat. So then just point everybody to that paper too as another example for flare changes during magnetic field.
I think Jaimine had published about half a dozen papers from about 1992, I think that paper was, through 2005 or so.
Right. Okay, that's all we have for questions that I see so far. So thank you, Brian. Very nice talk. Always interesting to see what's happening.
Thank you.
Our next